Welcome to the TOEFL Listening section. In this section, you will listen to an academic lecture and then answer questions about what you heard. You may take notes while you listen. You will have time to review your notes before answering the questions. Listen to part of a lecture in a university class. You will hear the lecture only once, so listen carefully. After the lecture, you will answer some questions about what you heard. Some questions ask about the main ideas and supporting details. Other questions ask you to make inferences or connections between ideas. Answer each question based on what is stated or implied in the lecture.
Good morning, class. Today we will examine three fundamental processes of the water cycle that hydrologists study closely: evaporation and evapotranspiration, precipitation, generation, and distribution, and groundwater flow and recharge. I will start with evaporation, which is the phase change from liquid water to vapor at the surface. Evaporation depends on available energy, air temperature, humidity, and wind speed. In vegetated landscapes, we usually talk about evapotranspiration, which includes plant transpiration. As a concrete example, in semi-arid basins, daily potential evaporation can exceed 5 millimeters per day during summer months, while temperate regions may see 2 millimeters per day. These numbers illustrate why evaporation can dominate the water budget in dry climates. Wind increases evaporation by removing the humidity layer above the water surface. High temperature increases vapor pressure deficit and accelerates phase change. Both factors together make evaporation highly sensitive to meteorological conditions. Turning to precipitation, we need to distinguish intensity, duration, and type. Rain versus snow matters, because snowmelt changes timing of water input into soils and streams. Intense short storms often produce more surface runoff because soil infiltration capacity is exceeded. Orographic effects are another important case study. In mountainous regions, uplift forces air to rise and cool, which promotes condensation and often enhances precipitation on the windward slopes. This spatial variability matters for how much water reaches streams and recharge zones. Interception by vegetation and surface storage, such as puddles or snowpack, delay the delivery of precipitation to soils. Interception reduces the effective precipitation that contributes to infiltration and runoff, and so it alters local budgets. Now, groundwater flow is a hidden but critical component of the water cycle. Water that infiltrates past the root zone percolates to the saturated zone and becomes groundwater. Recharge rates depend on soil permeability, fracture networks in rock, and the intensity of recharge events. We frequently use Darcy law to quantify groundwater flux. Darcy law relates flow to hydraulic conductivity and the hydraulic gradient. This gives us a practical way to estimate how quickly water will move through an aquifer given measured properties. A useful case is the Ogallala Aquifer in the central United States. Recharge is very slow relative to extraction because precipitation is low and much of the rain evaporates or runs off before percolating. Deep infiltration is limited, so groundwater storage declines over decades. Groundwater flow timescales can be long, from months to millennia, depending on hydraulic conductivity and the distance to discharge zones. This means groundwater acts as a buffer that sustains base flow in streams during dry seasons. Even though groundwater flow is often slow, it sustains base flow in streams during dry months and transports dissolved nutrients and contaminants over long time scales. To synthesize, evaporation and evapotranspiration control how much water leaves the system at the surface. Precipitation delivers water in different forms and rates and determines runoff versus infiltration. Groundwater flow stores and slowly redistributes water and links upland recharge areas to streams and springs. When we analyze a watershed, we quantify each process using measurements and models. Evaporation is measured with lysimeters and estimated with energy balance methods. Precipitation is gauged, and radar provides spatial detail. Groundwater is characterized with wells and pump tests combined with Darcy-based calculations. In your field projects, I want you to pay attention to how these processes interact. For example, a high-intensity storm on a dry, compacted soil will produce quick runoff and little recharge. Conversely, a gentle, prolonged rain on permeable soil can significantly recharge the aquifer. That concludes our overview of the water cycle processes. Evaporation, precipitation, and groundwater flow are distinct processes, but they are tightly coupled in any real hydrological system.
Listen again to part of the lecture, then answer the question.
Even though groundwater flow is often slow, it sustains base flow in streams during dry months and transports dissolved nutrients and contaminants over long time scales.
This concludes the listening section. For more TOEFL practice tests and study materials, visit spinta.org.